In this lecture, we'll talk about the condition for the two particle exchange. So there is exchange of particles between the two subsystems. Okay, and the particles are again the two subsystems that are two phases of the same substance. In this lecture, we'll talk about the condition for the equilibrium of two subsystems. In this lecture, we'll talk about the condition for equilibrium of two subsystems under particle exchange, where the subsystems are two phases of the same substance. Okay, so the example of the subsystems that are two phases of the same substance is ice melting in liquid water. So when ice melts in liquid water, there is exchange of water molecules between the two subsystems. Okay, so there's equilibrium between ice, water, and solid ice. And here we consider that the subsystems are enclosed in a rigid adiabatic wall where heat cannot escape or enter the system. So this is about phase equilibrium. Between two subsystems. So let's consider that we have two subsystems that are enclosed by an adiabatic wall. So that's the adiabatic wall. Okay, and this is the partition between the two subsystems. So subsystem A is in phase A and subsystem B is in phase B. So phase A of the subsystem is defined by temperature A, pressure A, volume A, internal energy of A, and number of moles A. Okay. Likewise, phase B or subsystem B is defined by temperature B, pressure B, volume B, internal energy B, and number of moles B. Since there can be heat and particle flow between the two phases or across the boundary between the two phases, the boundary will move and the boundary will evolve as the process undergoes. Okay. So the different kinds of interactions are subjected to the following constraints. So the constraints during the interaction between the two phases are the total number of the particles is always constant, although there can be change in the number of particles in phase A and phase B. Okay, sometimes phase A may have more number of particles than phase B, or sometimes B may have more number of particles than A, but the total number is always constant. Okay. This comes from the fact there is conservation of mass. Mass can neither be created nor be destroyed. and then the volume is also constant. Again, sometimes phase A may have higher volume than phase B may have higher volume than phase A, but the total volume is always constant. Okay, and these are the things that I meant when I talk about the shift in the boundary. Okay, also there is constant internal energy in the whole system. Sometimes phase A may have more internal energy and phase B. Other times B may have more internal energy than phase A, but the total is always constant. And we know that from the first law of thermodynamics. So du is dq minus pdv. Okay. So there is no heat entering or leaving the system, so this is constant, and also the total volume is constant, and that makes this du also constant. Okay, or I should say this dq is 0. There's no heat entering or leaving the system, so that means q is constant, and dv is 0. There's no change in volume, that means v is constant, and du would also be then 0 because these two are 0, so that means u is constant. Now we know at equilibrium, once phase A and phase B reach an equilibrium state, what happens to the entropy? So at equilibrium, entropy is maximum. That's what we learned before. Okay. So that means since S is extensive variable, so that means SA plus SP, the entropy is the sum of the individual entropies, would be maximum. Okay. Now let's change all the variables that define the subsystems by infinitesimally small amount. So let's say now our entropy is increased by small amount ds, then the small change in entropy would be given by small change in entropy of A plus small change in entropy of B. But we know that from the combination of first and second laws, TdS heat is given by change in internal energy plus pdv minus mu dn. Okay. So that means change in entropy of A would be given by 1 over temperature of A. Okay, just taking this T to the denominator, du of A plus PA dVA minus mu A dNA, and then for B, the change in entropy by infinitesimally small amount would be 1 over TB dUB plus PB dVB minus mu B dNB. So then we can eliminate the three infinitesimals by invoking our three constraints. The three constraints are this dn plus dnb is equal to 0, because the total change in number is 0. There is no change in total number. And dva plus dvb is equal to 0, and dua plus dub is equal to 0. So we can write this as dna is equal to negative dnb, dva is equal to negative dvb, and here dua is equal to negative dub. So by combining these two equations with these three equations, we can write so we have dsa plus dsb is 0, okay, because ds is 0 when the states are in equilibrium. So then we can write this as 1 over ta dua is negative dnb minus pb pa dvb dva. We are looking at the first one. So dua no, so that's not du, that's not dn, that's du. That's the first term. Okay, dua is negative dub, and dva we can replace that by negative dvb, and then dna could be replaced by negative dnb. So negative and negative is positive, mu a dnb minus, and then we have this thing for dsb, so 1 over tb negative that's positive dub plus pb dvb minus mu b dnb, and that's equal to 0. So we can put the common terms out of the parentheses. So 1 over tb, so this and that. So let's see, one of the terms should be no, this is positive because we are adding the two. So 1 over tb minus 1 over ta, and then dub is common to both the terms, plus pb minus pa, and then dvb is common to both the terms, dvb, and then we have this term plus mu a minus mu b dnb is equal to 0. So these variables u, v and n are all independent. That means these must be independently equal to 0. Okay, so that means 1 over tb minus 1 over ta must be equal to 0. That implies that tb is equal to ta, which means that once they are in equilibrium, they would have same temperature, so they would be in thermal equilibrium. Okay, and then the second one will give us pv minus pa is 0, so that implies that p B is equal to PA, so that means there is also mechanical equilibrium. And then the third one is mu A is equal to mu B, which means that if the system is in equilibrium, there is thermal equilibrium and mechanical equilibrium, and there must also be chemical equilibrium. There must not be any kind of mixing of the substance. Okay, they must be staying as it is. There shouldn't be any diffusion or any kind of chemical reaction. Diffusive equilibrium. Okay, so we can say that if we have two phases, or which could also be two subsystems, like ice, water, and ice, not two substances, sorry, subsystems. In thermal and mechanical equilibrium, then there must also be in diffusive equilibrium. Okay, that means there is no exchange of particles or chemical reaction. Okay. Now let's say that the two subsystems have not reached the mechanical equilibrium yet, or equilibrium yet. Okay, so they are yet to be in equilibrium. So suppose the two interacting subsystems, I don't know why I'm writing substance here, subsystems are not yet in equilibrium. That means the total entropy of the system has not reached maximum yet. Okay, so S has yet to reach equilibrium. H is reach maximum. So S is maximum only when the total system is in equilibrium. So that means then delta S, which is SA plus SB, would be greater than 0. Okay. So let's consider a state, okay, that is very, very close to reaching the equilibrium. It is away from the equilibrium by very small amount, or infinitesimally small amount. That is very close to equilibrium. Okay, so it's away from equilibrium due to an excess of that much mass. in subsystem A. So once this mass is equally distributed, then the system will be in equilibrium. Okay, and this is the excessive mass in A, whereas the same mass would be deficient in subsystem B. Okay, so negative delta S, delta NA, mass deficit in subsystem B. So once this mass is transferred to subsystem B, then the system would be in the combined system would be in equilibrium. So that means as the combined system moves towards equilibrium, so the subsystem A will give up its excess mass, which is delta NA, to subsystem B. Okay, so as the subsystem A gives it excessive mass to subsystem B, there would be change in entropy, which would be given by change in entropy, which is given by delta SA is mu A over T. We saw that the heat involved is mu times number in this case is delta NA, and it's negative because it's the decrease in the number. Okay, so that's the heat, and T over T gives the entropy. Okay, and likewise the change in entropy in system B would be given by delta SB is negative mu B over T times the number. Okay, here it's delta NA positive because it's gaining the number, so it's positive. And in both cases, as they reach the equilibrium, because it's very small change, so we consider that the temperature doesn't significantly differ between the two subsystems, so we can just consider the temperature is T for both the subsystems because this is very small. They're almost near the equilibrium. So then the total entropy, once they are they reach the equilibrium, these two would be, the sum of these two would be 0, but since they are yet to reach the equilibrium, so it's so they are not yet in equilibrium. So that means delta SA plus delta SB is greater than 0. So delta SA is mu A over T, mu A delta NA plus over T plus mu B delta NA over T, that's negative, is greater than 0. So then mu this thing is common to both the terms. If we just take the common and then divide both sides by that term, then we'll get rid of that. So then what will be left is mu a minus mu b is greater than 0, and then that gives us mu a is greater than mu b. Okay, so this is the condition when the system is not in equilibrium and there is like exchange of particles. So this is condition required for exchange of particles that are yet to be in equilibrium. So for the particles to be for the particles to exchange between the two subsystems, the chemical potential between the particles should be unequal. One should have greater chemical potential than the other. Okay, so thus in the approach to equilibrium, heat energy must flow from the hotter to the cooler body, and then volume will be gained by the body under lower pressure at the expense of the other. And the implication of this one is the mass will tend to flow. Okay, this comes from this fact again, from the body of higher chemical potential towards the one of lower potential. Okay, so now let's talk about Gibbs phase rule. When there are multiple particles in a system, so Gibbs phase rule so this is the rule for equilibrium between multi-constituents or multi-particles, different kinds of particles. And these multi-constituents also may be in multi-phases. Okay, for example, you may have water and nitrogen and oxygen mixed. So these are multi-constituents, and these may also be in different phases. So water may be in vapor and liquid phase. Nitrogen may also be in vapor and liquid phase. Oxygen also may be in vapor and liquid phase. So these are multi-phases and these are multi-constituents. So if we consider a single phase, then the Gibbs function is given by, we know from the previous discussion, for a single phase the Gibbs function is given by sum of chemical potential times the number of particles. So J goes from 1 to m, okay, some number m. So this is for single phase, okay, and each J represents one constituent. Okay, so we have, like, we may have J is 1 for, let's say, water, and J is equal to 2 for nitrogen, J is equal to 3 for oxygen. Okay, so as many as so J could be any number of constituents. Now if we have multi-phases also, okay, so let's say for a system with, let's say, ith constituent, okay, like water, nitrogen, oxygen, we have ith constituent, and rth phase, okay, so we can have vapor, liquid, in some cases we may have solid, okay, in rare cases we may have all three phases. In that case, the Gibbs function is given by G is sum over all the constituents, so I goes from 1 to k, and sum over all the phases, say gamma goes from 1 to pi. Okay, pi here is not 3.14, it's just the symbol for number of phases. So mu I, and then gamma for the number of phases. Okay, so here mu I gamma is the chemical potential of the ith constituent, which is in gammath phase. And n in this case is the number of kilomoles of the ith constituent that is in gammath phase. Okay, basically if you are considering oxygen, like here oxygen in liquid phase, for this particular constituent in this particular phase, this n I gamma would be number of moles of that. Okay, if you put the things in a table, it would look like this. So we may have phases given by say alpha, beta, gamma, and all the way to pi. So these are the phases we have, and then we also have constituents. So we have constituent 1, constituent 2, constituent 3, 4, all the way to k. So for ith constituent and alpha phase, we'll have the Gibbs function n1, sorry, not n, mu1 n1 alpha alpha. For this one, we'll have mu1 n1 beta beta. This one mu1 n1 gamma gamma. Likewise here we have mu2 n2 alpha alpha, mu 2 n2 beta beta. Okay. So when you add all when we add all these things, we get the total Gibbs function. Gibbs function is sum of n I mu I gamma gamma. So when the system reaches equilibrium, for equilibrium, we saw that this dg, keeping temperature and pressure constant, would be 0. So that means we can apply that to our Gibbs function. So dg at constant temperature and pressure, using the product rule here, so we can write summation I goes from 1 to k, gamma goes from 1 to pi, so ni gamma d mu I gamma. So just taking the differential for the first one, and then we'll take the differential for the second one. Gamma 1 pi k, so take the differential of n, keeping mu constant. Okay. Now we know that from the previous discussion, this thing would be 0 when we keep temperature and pressure constant. Okay, so something that we already got before. So mu I gamma di gamma is 0. Okay, so let me see where we got that. I will put the reference here. So we got that in equation 915. Okay, so this is from equation 915 from the textbook. Now if that is true, then using that in this expression, we get, because dz is 0 for equilibrium and this thing is 0, that means this must also be 0. So this sum I from 1 to k and gamma from 1 to pi, ni gamma d mu I gamma is 0. Okay. This is true when the system is in equilibrium and keeping T and P constant. Okay. Now if the transfer of mass of a constituent, for example the ith constituent, occur between its different phases within a closed system, then we saw in the previous discussion that the total change in the number would remain same, okay, for that particular constituent, because the total number of moles of that constituent is always constant. No particle is entering or leaving the system, although there is change in the number between the different phases, but for that particular phase, for that particular constituent, the total number is always same. Okay, for an exchange of particles between different phases of a constituent, this total number or change in total number of that particular constituent is 0. Okay, this is for this particular constituent, this ith constituent. Okay, just like we saw before, that this dna plus dnb. Okay, this is change in A and change in B. The total change would be 0. Okay. Likewise here, again there is change in different phases. Number of particles in different phases are changing, but the total change for that particular constituent is 0, because there's no actual change in the entire system. And again, this comes from the fact there is conservation of mass. The mass of the entire system is always conserved, although there is change between the subsystems. Now let's consider just the two constituents and two phases for simplicity. So consider two constituents. Let's call them I1 and 2, and two phases. So say it's phases alpha and gamma, alpha and beta. So we have phase alpha, phase beta, constituent 1, constituent 2. So then this thing then would be n1 d mu 1 alpha alpha, n2 n1 d mu 1 beta beta, n2 d mu 2 alpha alpha, n2 d mu 2 beta beta. Okay. And some of these things would be that. Okay, so we have mu1 alpha dn1 alpha plus mu2 just a second. So here let's not this one, but let's consider this equation. Okay, we want to find the condition for equilibrium. So rather than this one, we'll consider this case here. So we'll use not that, but mu dn. Okay, mu dn. I mean, we can get something from this also, but here we want to find a condition in terms of chemical potential. So I'm writing this mu dn. So mu dn, mu2 dn2 alpha alpha plus mu1 dn1 beta beta plus mu2 dn2 beta beta. That's 0. Okay. And also from this condition, change in 1, there will be some change in alpha, plus there will be some change in beta phase, but the change in entire constituent would be 0. Likewise, dn2 plus dn2 alpha beta would be 0. So we can use this expression in that and this expression in that. So what we get, so mu1 alpha, so dn alpha is negative dn1 beta plus mu2 alpha, dn2 alpha is negative dn2 beta plus mu1 beta dn1 beta plus mu2 beta dn2 beta, that is equal to 0. So dn1 beta and dn1 beta can put outside the parenthesis, so negative plus mu1 beta dn1 beta, and then minus, or we can write plus here, so mu2 beta minus mu2 alpha dn2 beta is equal to 0. So this dn1 and dn2 are independent quantities, they are different constituents, so that means the coefficient of those independent variables must be independently 0, okay, if that entire thing is 0. So that means this implies mu1 beta is equal to mu1 alpha, and this implies mu2 beta is equal to mu2 alpha. Okay. So that implies that the chemical potential for the two phases of each constituents are equal when the systems, when each of the constituents are in equilibrium with T and P fixed. Okay. Okay, so that's all for this lecture. We'll continue this in next lecture.